Welcome to Analog Electronic Circuits lecture number 9, and today we are going to discuss about the high frequency model of a BJT. High frequency model of BJT. So all of you all take your notebooks and draw the high frequency model of a BJT along with me. It's a very important concept. Okay, so first let us draw the mid-frequency model, hybrid pi model of the BJT. So how does it look like? So here we have, let me draw the symbolic form of it first. So if this is my BJT, this is my base, this is collector, and this is emitter. So how does the model looks like? At mid frequency. So at mid frequency, you all have over here, let's say this is the base, this is the collector, and that's the emitter, right? So what is there between this? Let me mark over here. This is base, collector, and emitter. So what is connected between base and emitter in hybrid pi model? There is a resistor R pi, and the voltage drop across this resistor is V pi. Between collector and emitter, we have a current source, a voltage dependent current source, and it's given by Gm into V pi. Okay, and also we have RO or RD, whatever you wish to call it. So let's call it RO, which is the output resistance of the BJT, correct? So that's what we have seen. This was the mid frequency. Let me just write emitter properly. And whenever my voice breaks, please immediately inform so that I can stop and repeat that concept again. I hope my voice is audible now, clearly. Yeah. So far we have studied the mid-frequency hybrid pi model, right? Now we will see how will the high frequency model look like. So for a high frequency model, there are some capacitors which are present over here. So we have one capacitor connected between the base and the emitter. That capacitor, we will mark it over here. This is called as CBE, or it is also famously called as C pi. Okay, it has another name. I will be talking about it. There is a capacitance, parasitic capacitance present between base and emitter. I will tell about its origin very shortly now. One more capacitor is there between the base and the collector. So there is one capacitor over here connected between the base and the capacitor. You can call it CBC, or it is more famously called as C mu. So C mu, right? And there is one more capacitors in modern BJT structures. There is one more capacitor over here connected between the collector and the substrate. Substrate is normally connected to the ground. It is called as CCS. Okay, so please complete this now first. Complete it in your books. So there are three additional inter-electrode, or we can say parasitic or stray capacitance, which are present for a high frequency model in of a BJT. So if I want to represent them in the BJT symbol, I can represent them as follows. So over here we have, let me just have it over here. Okay. Let me cut this and call this as emitter. Okay, fine. I'll represent it over here. Between the base and the emitter, I have CBE, small CBE. Between the base and the collector, I have CBC. And between the collector and the ground, I have CCS. I'll talk about that a bit from now. Please concentrate now. So I will talk about the origin of this capacitor in brief, or of these capacitances in brief. Okay. So let me draw the structure in detail. I will be sharing a recorded video wherein I will explain the origin of each of them in detail. Right now we will focus on a short knowledge of them. Okay. Let me just draw that structure now. So this is how the modern BJT structure looks like. So here we have integrated circuit form. It's in the form of integrated circuit. So first we have a layer of emitter, then we have a base, then we have collector, and finally we have the substrate. Okay, so that's how the structure looks like. This is my this we can call it as N plus, then this is P, this is N, and this is P plus substrate. This is P plus substrate. And if I want to mark the connections over here, I can mark it like this. So in a modern BJT structure, all the contacts are taken from the top. Okay, so this becomes my emitter. This is my base, and this is my collector. So you might have studied the planar structure in this form, right? Planar structure is in this form. So you must have studied in this manner in your lower semester. That is also not, in the earlier discrete circuits, we used to do it this way only. But now in integrated circuit, this is the structure. So here was the emitter, then the base. We have the base and the collector. So this is the planar structure, and this is the modern BJT structure. Modern BJT structure, and this structure is used in the integrated circuits. Okay, this is the structure which is used in the integrated circuit. Now to understand the origin of these capacitors which are present, which you see over here, the CBE, CCE, CBC and CBE and CCS, let's understand, we should know the PN junction theory very well. So even in the planar structure, if I write over here, this is N, P, N. I mean, we can write N plus P, N, right? We know that whenever there is a PN junction, there will be a formation of a depletion layer. So this is the depletion layer present over here. Another depletion layer present over here. And there will be a depletion layer. This is your base to emitter junction, right? And this is your base to collector junction. So there will be another depletion layer present over here. Now, can you tell me which depletion layer width will be more? Which depletion layer width will be more? Let me call this width as WB, and let me call this as WC. The width of the base collector depletion region will be more, or width of the base emitter depletion region will be more?
So base collector.
Yes. So basically the base collector depletion region width will be more, because we know that from the PN junction theory that in the reverse bias the depletion region width keeps on increasing. Correct? So there are two junctions over here. We call them as base emitter. So JBE, and here we call it as JBC. Base emitter junction and base collector junction, right? And normally your base collector junction is forward bias. This is forward bias. And this is reverse bias. Base connection in a BJT is reverse bias. So this is the forward active mode of operation, if you recollect. Okay. So what happens is, in a diode, we know that in the reverse bias, as we go on increasing the voltage across the reverse bias, the depletion region width also keeps on increasing. Yes or no? So let's say if this is a PN junction, if this is a PN junction diode, okay, and this is the N side, and this is my depletion region marked in blue color. So let's say in our case, this is the base collector, the PN junction between the base and the collector. Okay, so let me slightly move it up. So what will happen if I increase the base, if I increase the base collector voltage? What will happen to my width over here? Let's say it is WC. What will happen to that? Your WC will increase. Correct. So and depletion region is consisting of what? What is depletion region consisting of? It is void of any carriers, right? So this is your depletion region. So depletion region doesn't contain any carriers at all. It is void of carriers, right? So what is happening over here is this thing. This is on the base side. We have P and N, right? We have a base and collector. I'm just drawing the exaggerated version of this diagram. Base and collector. Okay, to explain the concept. So what will happen is if I increase the base to collector voltage, my width of the depletion region will increase. Fine. So this will act as a capacitor. Your diode, your PN junction diode will act as a capacitor. Where what is the dielectric over here? Your depletion region act as the dielectric. Your dielectric is nothing but your depletion region. And the P side of the plate is acting as a positive plate, N side is acting as a negative plate. So it is behaving as a capacitor. Now, what is the formula for a capacitor? C is equal to dq by dv. So as I change my value of voltage, the charges also changes, right? Charges also changes. So that is existing. I mean, there is a capacitance existing between the base and the collector. So that is called as CBE. That capacitor is called as CBE, or it is also, CBC. Sorry, and it is also called as C mu, or it is also called as transition capacitance. So it has three names: CBC, C mu, and CT. It is called as transition capacitance. So this is the information and the origin of C mu or CBC capacitance, which is there. Any doubt in this? I've kept it as short as possible. Any doubt over here? Okay, fine. Now let's see the origin of CBE. Now I will draw this C mu or CBC between here only. So here we have, let me draw with red color. So this is my base and this is my collector junction. So this is my CBC. Now my base emitter junction is forward bias, right? My base emitter junction is forward bias, so there will be a capacitance associated with that also. CBE. Now you will say in forward bias, how does the capacitance exist? I will come back to it. And there is one more capacitance due to the structure itself. Now remember here we have P plus N junction. So again that P plus N junction will be reverse bias. Correct? So this another capacitance exists, which is CCS. And what is CCS? CCS is the capacitance between, let me write over here. CCS is the capacitor or capacitance between collector and the substrate. Between collector and substrate. Okay, and so that exists. CCS exists due to the modern BJT structure, where all the contacts are taken from top. This fourth contact we can call it as a substrate. Okay, so this contact over here is my substrate. All the contacts in integrated circuit form are taken at the top. Okay, so that's the substrate contact, and that is normally connected at the top. All the contacts are taken from the top, and the substrate contact is always connected to the ground. So this substrate contact is normally connected to the ground. Fine. Clear about this? What is CCS? I have drawn this capacitance over here between the P plus N junction. That is also a reverse bias. So whenever there is a reverse bias, there will be existing a capacitance. But why? What is the existence of the CBE? Of the CBE? Now you all know that in a BJT, the current is flowing due to drift or diffusion. Can you tell me what is drift?
So
What
drift
is
is due
drift?
to applied voltage.
Correct. And diffusion?
So diffusion is because of the change in concentration of carrier particles.
Perfect, perfect. So drift is due to voltage gradient. Drift is due to voltage gradient. Wherever there is a difference in the voltage at one point and other point of the semiconductor, and diffusion is due to concentration gradient. Concentration gradient. And in BJT, which is dominant, in BJT, what do we have? What is dominant in BJT? Anyone? Your diffusion is more dominant in BJT. Why? Because there is large change in concentration. Let me explain. So here it is N plus, this is P, and this is N. So let's say the concentration of this is my BJT. Okay. Here is my let me mark the terminals quickly. Here is my emitter. We know emitter is the heavily doped, right? You all know the reasons about it. The base is very thin and lightly doped, and collector is moderately doped and very large. Okay, so here the concentration of N plus is the N-type impurity, right? So that N-type impurity is around, let's say, 10 raised to 18 per centimeter cube. P-type, let's say the concentration is around 10 raised to, let's say, 15 per centimeter cube. And for collector, let's say it is around 10 raised to 16. So what are the majority carriers in N plus region? What are the majority carriers over here in N plus? Electrons, right? Majority carriers in P region, holes. And again, the majority carriers in N region over here, again the electrons. So over here, whenever electrons tries to diffuse over the base emitter junction, they will leave behind holes, right? So what is happening is electrons are going into the electrons which are majority carriers are going into a minority carrier base region. Okay, so the current will flow due to drift phenomena, diffusion phenomena, because there is a large concentration change between the electron concentration in the emitter and the electron concentration in the base, because base are minority carriers. Okay, so what do you mean by majority and minority? Majority means, let's say you have 10 raised to 18 per centimeter cube, this many carriers. And minority carriers mean there will be around, let's say, 10 raised to 4 per centimeter cube. So very, very small number of minority carriers exist. But since there is a change of large concentration to low concentration over here, the current which flows is diffusion current. So we say electrons diffuse from emitter to base region. Okay, and holes from the base diffuse from base to the emitter region, or the electrons from the collector region diffuse across the base collector region and moves towards the base. Fine, are you understanding this? Some of them recombine in the base, and the remaining of the electrons will be passed or will be drifted towards the collector region. Understanding this? So what happens is, whenever such diffusion phenomena takes place, if I draw a profile, concentration profile. So here is my concentration profile over here. This is my emitter, that's my base, and that's my collector. I guess you must have studied this concentration profile. So due to diffusion phenomena, this is the minority carriers, and these are the minority carriers over here. Okay. So basically, why minority carriers? These are holes. Holes in N-type region are minority carriers, right? And these are electrons. So what happens in a forward bias PN junction? So in a forward bias PN junction, when VBE is the base emitter voltage. So if VBE increases, your electron, the electrons diffuse more towards the base, and the holes diffuse more towards the emitter. Okay, so what will happen? The electron and hole diffusion takes place heavily over here as we go on increasing the VBE. So this will go normally at low frequency. They will have no problem at all, because there is a minority carrier diffusion taking place. Okay, because electrons are getting into the base region, and holes are getting into the emitter region. And in this space over here is my depletion region. This green color space over here is my depletion region. Base emitter depletion region and base collector depletion region. So what exactly is happening is, at low frequency there is no problem. At low frequency there is enough time for the electrons, which are minority carrier electrons and minority carrier holes, to diffuse across the junction. There is no problem with that. Problem arises at higher frequency. Okay, so problem arises at high frequency. Why does the problem arise at high frequency? At higher frequency, the time required for the electrons to diffuse will be very, very less, right? And that time is called as transit time. Transit time. So transit time at high frequency is very, very low. Low time for the minority carriers are very low in consideration, right? And if your circuit is working at a very high frequency, then there is less time for these minority carriers to diffuse across the junction. So what will happen? Because it will take some time, few of these minority carriers will be stored at the emitter side of base emitter junction, and few of these electrons will be stored at the base side of this base emitter junction. And there will be a storage of, or there will be an accumulation of charge carriers over here, right? So it will be again acting as a capacitor. So here we have a capacitor in between. In between we have a base emitter junction, so that will act as a dielectric. This will act as a dielectric. Okay, and the two sides of the plate will be this storage of charges, which is holes and electrons, right? So here we will have positive, and here we will have negative. The only difference is this capacitance exists in the forward bias region, right? And it will be very, very dominant only at higher frequencies. Fine, because electrons and holes, minority carrier electrons and holes, will take some time to diffuse across the junction. So by the time they do so, they keep accumulating at the depletion region. So those accumulate as charges, right? And that's why we know already now, I've already told you all that capacitor will be given by dq by dt, dq by dv. So if you increase your voltage, if there is a change in the voltage in vb, the charges will be changed. There will be change in the charges, and that will lead to capacitance. So this capacitance is called as cbe, or it is called as c pi. Sorry for this. C pi, or it is called as cd. It is called as diffusion capacitance. Okay, so please write it down. This is called as diffusion capacitance. Is this point clear to you? How does capacitance exist? Any doubt over here? This will happen at high frequency only. At low frequency, this phenomena will not exist. Okay, so that is what the origin of these three capacitances are. So now you have, and these capacitances are in picofarad range. Their range is in picofarad. So why they are not affecting in low mid frequencies and low frequencies? Anyone has an answer? Why they are only acting up in high frequency? So at high frequency, let me write it at high frequency. Why does capacitors exist? F is around several megahertz or even higher, correct? F is in this range. So what is the reactance offered by the capacitance? These capacitances, let's say Xc will be 1 upon 2 pi. Let's say it is around 100 megahertz into, let's say the value of these capacitances over here, these are called as parasitic or interelectrode or stray capacitances. So let's say the value is 1 picofarad. Can anyone tell me what's the product of this 1 upon 2 pi into 100 mega into 1 picofarad? We are calculating the reactance, impedance offered by this capacitor. 1 divided by 2 pi into 100 mega hertz into 1 picofarad. 1 pico is 10 raised to minus 3. What's the number which you get over here? Anyone? I think I'm getting around 6 ohms approximately. Yeah? This is approximately 1600 ohms. So you see, this is neither zero nor it is very high value. So it is a moderate value. So that's why we cannot ignore it at higher frequency. So what will happen at low frequency? What will happen at mid frequency? We'll see. At mid frequencies, this will be around let's say hundreds of kilohertz. So for this, if we want to calculate, okay, this is a problem. Let me just change the setting. Yeah, now it will not occur. At around 100 kilohertz, can anyone calculate this XC and let me know? It will be, let's consider it to be 100k, 100 kilohertz into 1 picofarad. Let's say that this parasitic capacitance have a value of 1 picofarad. Can anyone tell me this number? 1 divided by 2 pi into 100k into 1 picofarad. How much is the number over here? 1.59 into 10 raised to 6 ohms, which is very, very high value. This is a high value. So that's what happens is these capacitances, which are called as stray capacitances, are considered as open circuit. So we can write over here, therefore, the stray capacitances at mid frequency, let me write mid frequency as MF, are open. Stray capacitances at mid frequency are open circuited. Okay, whereas at higher frequency they should be considered. So stray capacitance are considered, means they will be active, considered at high frequency. Why? Because the impedance offered by these capacitance will be very, very, moderate value, not very high, not very low. So you should remember this, the stray capacitance are considered at high frequency. Now if you go to low frequency, similarly, if you low frequency meaning what? Let me write over here, low frequency range. At low frequency, you can easily calculate F will be in the range of few hertz, or let's say hundreds of hertz. That's it. Now we definitely know that if that happens, your XC will definitely be very, very high. It will be tending towards infinite, or we can write over here very, very high. We know that. So again, the same thing will happen. The stray capacitors at mid frequency will be open. At low frequency will be open. So we can write over here stray capacitance, and these stray capacitance I will let you know what are they in above. It is all the three capacitance which are marked over there. LF stands for low frequency, are open. Okay, that's why we study them only at high frequency, not at mid frequency, neither at low frequency. Correct? So here it is. These are the stray capacitances: C mu, C pi, and CCS. You have any doubt in understanding this concept? This was very, very important. Understanding the high frequency model of a BJT. Any doubt in this? Anyone? Okay, excellent. Now, next I will be talking about the wiring capacitances. So if you are writing along, you can write it along. Next is wiring capacitances. These are also another kind of a stray capacitances, and their values are also very, very small in picofarad only. So what normally happens is, let's say that you have a BJT, right? And here is my collector, base and emitter, and I have my ground over here. Okay. And I want to, use this as an amplifier, directly use this as an amplifier. I am not drawing the remaining part of the circuit. Please understand, I'm not drawing the amplifier part. It's assume that you already have that. So let's say this is my amplifier part, and this is my AC input. This is my AC input at very high frequency, hundreds of megahertz, right? And this is my AC output. So this is my AC output over here, okay, plus minus. And we also apply DC, yes, DC we also apply over here to power the BJT in the forward active mode. So I'm not drawing the remaining part of the circuit. So what happens is, in reality is, see, this is ground. This is either we can call it as a AC ground or a DC ground, but this is a ground. So what happens is that this is my base terminal, this is the collector, and that's the emitter, right? No need to show that over here. So what happens in reality is, these are wires, right? You connect the input signal, via a wire, right? Via a wire to the base terminal of your BJT, and this is another wire over here. Okay, so between these two wires, there will be existing a capacitor at high frequency, and this capacitor which is output wiring capacitor, because from the collector terminal to the load, you are connecting a resistor and a capacitor, external capacitor, right? So and resistor also over here, right? You have collector, resistor RC, then you have RL. Yeah, you connect that with a wire. So these are wires actually. All these things are wires. This is also wire. This is also wire, and this is also wire. So what is the problem? Why does capacitances exist? Anyone can guess? Anyone wants to guess? Yeah. So this is a wire. This is a wire, and here we can say the air can act as a dielectric. So we can say between two wires, air act as a dielectric. Now, so air as dielectric. Now, can you tell me any two wires in the circuit are at same potential over here? Is the wire at over here at the same potential as this, or at the wire over here is at the same potential over this? So which potential is higher, over here or here? At the top or bottom? Can you tell me, at the collector potential is higher, or at the emitter potential is higher?
Sir, the collector.
Okay, so we can say this is the wire at a high potential. This is the wire at low potential. Okay, so here we have a wire, and this is at a higher potential, much higher potential, and we have AC. AC means it will keep on changing. So that means cumulatively, if we want to say, we can consider the two wires at different potential. In between, we have a air as a dielectric, and these charges are changing. There are negative and positive, because this wire is at a lower potential, this wire is at a higher potential. So at very high frequency, when this happens at a very high frequency, let's say somewhere around frequency of around, let's say 500 megahertz, then this capacitance will come into existence because of these wires. Because these wires will act as a conductors, and air as a medium, they will be soon turning up into something called as wiring capacitances. So over here we have CWO. Understood this concept about wiring capacitances, everyone? Any doubt in this? They exist at higher frequency due to different potentials. And over here, CWI is called as input wiring capacitance. Input wiring capacitance. And CWO is my output wiring capacitance. CWO is output wiring capacitances. And these are also called as stray capacitance. And their value is around in picofarad again. Okay, their value is in picofarad. And they are also called as stray capacitances. Okay, understood this? Any problem? So at higher frequencies, we should consider all of them in a BJT amplifier. So now, so far I will revise what we have done. Yeah, so we were started with the high frequency model of a BJT, and high frequency model is nothing but mid frequency model plus the parasitic capacitances, which is C pi, C mu, and CCS. And we have seen each of them origin also. We have seen why they originate in the first place due to the modern BJT structure. And we have seen that why only at high frequency they are active. Why not at mid frequency? Why not at low frequency? We have used numbers to support our claim. Next, we saw the concept of wiring capacitances, why they exist, and how at higher frequencies they will also contribute. The same reason will be valid over here also. These wiring capacitances will be active at higher frequencies only because they are also in the same range, picofarad only, right? So again, when the range is picofarad, the stray capacitances are considered at higher frequencies. So they will only act when at higher frequencies only. Fine. So now we will draw the high frequency response. We'll consider the high frequency response of a BJT amplifier. So let's start. Everyone draw along. High frequency response of BJT amplifier. So draw the circuit of BJT amplifier. Many a times we have seen that before. BJT amplifier circuit, kindly draw. So first of all, let's start with BJT itself. Then we have RC, RE, R1, R2. We connect them together. Here it is plus VCC, which is DC. This is R1, R2, RC, RE. Okay, and this is connected to the ground. Fine. Now we will connect the RSig and CC1, the coupling capacitor. So this CC1 is connected, externally connected coupling capacitor. So here it is RSig, and we have a AC source over here, plus minus Vs. At the output we have output coupling capacitor CC2, and we can have a resistor also at the output as a load. So that is RL, and here we have the output Vout. Anything is missing? Yeah, bypass capacitor is missing. Bypass capacitor was missing. This is CE. Okay, and what are their ranges? I mean, they are in the range of microfarad, right? CC1, CC2, and CE are in the range of microfarad. Now let's draw the wiring capacitance first. So from here to here, we have wiring capacitance between the ground. This is called as CWI. From here to ground, we again have wiring capacitance. We call it as CWO. Then we have capacitor between the base and the collector. Between the base and the collector, what is the name of this capacitance? Anyone? C mu. And between the base and the emitter, we have C pi. Fine. And there is one more capacitance between the collector and the ground, which is CCS. So this is my BJT amplifier with all the parasitic and the coupling capacitors and the bypass capacitors. So over here we can call CC1, CC2, CE are termed as externally connected capacitors. So now can anyone tell me why they are connected in the first place? Why do we connect CC1, CC2 and CE? You have a lab also, we have discussed so many, many times on this also. So why they are connected in the first place in BJT amplifier? Or will the BJT amplifier work without them?
Sir, they block the DC component.
Yes, basically we want AC and DC to coexist in the same circuit without interfering with each other. Okay, and your AC should not disturb the DC, neither your DC should disturb the AC. So for that, we have to connect the input coupling, output coupling, and the bypass capacitor. And all these capacitances are in microfarad range. Okay, and what are the other capacitances, stray capacitances, which we can write? C mu, C pi, CCS, CWI, and CWO. All are called as interelectrode. I mean, out of this interelectrode will be okay, let me use the black one, interelectrode capacitance. So out of that, interelectrode capacitances are these three. These are wiring capacitances. Okay, the other name is parasitic capacitance. Parasitic capacitance, or they also called as stray capacitances. And all of their ranges are, all of them are in the range of picofarad, few picofarads. Understood? As I've told you all in one of these starting lectures that wherever there is a capacitor, it is the speed killers. Or that is the reason why your amplifier is not able to amplify at low frequencies and at very high frequencies, right? Now all of you have done an experiment in for your BJT amplifier, I guess, right? So let me show you the frequency response now of it. Let me make, connect everything together so that you can understand. So here is my frequency response. This is my gain in dB, right? Gain AV in dB, and that's how my frequency response will look like. All of you all got similar kind of a response? Yes or no? In your labs. And then you went 3 dB down. This was A maximum or AV mid maximum. Then you went 3 dB down, and then you marked the FL, FH, right? This was the value FL, lower cutoff frequency, higher cutoff frequency. Basically, I will go one step further. So this region over here, let me mark it, right? This region over here, like this, from here to here. Let me mark it down. Yeah, up is also fine. This region over here is called as low frequency region. low frequency region. And this region over here, okay, from here to here is called as high frequency region. Okay, high frequency region. And in between, what do you have? Mid frequency. And last time I've told you all, at mid frequency, the gain of the amplifier remains almost constant. So you would like to operate your amplifier at mid frequency. For that, you should know the bandwidth, right? Now, what is the bandwidth formula? Anyone? Bandwidth is given by fH minus fL. So basically this range only. Now, anyone knows why does the gain fall at low frequency?
So because the bypass capacitors start acting.
Yes, a very, very important conceptual question. Huh? Why amplifier, right? The gain of amplifier fall at low frequency. So what's the answer? What's the answer to this question?
Sir, the bypass and the coupling capacitors start acting.
Yes. So the gain, why does the gain of the amplifier fall at low frequency? Due to externally connected capacitors. Due to externally connected capacitors. And what are externally connected capacitors in this case? It is CC, and we were finding FL of CC1, remember? FL of CC2 and FL of CC. What is that exactly? It is affecting the low frequency now. If these capacitors were not present, the gain would have not fallen. It would have remained flat. So the reason why the gain of the amplifier is falling at low frequencies is because of the externally connected capacitors. Is this point clear? Now, I have not taught this thing, but you will observe these things in the next one lecture, that why does the gain of amplifier, now this you have not experienced yet, but I will tell you the reason right now, fall at high frequency. Again, these are due to capacitors only, but which capacitance? They fall due to, write down the answer, due to parasitic or stray capacitances. Due to parasitic or stray capacitors. So what are they? C mu, C pi, then we have CCS, then we have CWI, then we have CWO. In short, the entire module number 1 teaches you this. The entire module number 1 teaches you this, right? This is a very, very important concept which people fail to understand many times and fail to answer also most of the time. Whatever we will be spending time on next 2 or 3 lectures will be to prove the second answer, that the gain of the amplifier fall at high frequency due to the parasitic or stray capacitances. Is this point very, very clear? Anyone has an iota of a doubt over here, please ask.